Hello viewers, welcome to Electronics India YouTube channel. In this video we are going to see about the basic optical laws and its definitions, and also we are going to see the concept of ray theory transmission. So before studying how the light actually propagates through the fiber, the laws governing the nature of the light must be studied. This was called as a law of optics or ray theory. When the light travels through a material, it exhibits a certain behavior explained by the different laws called reflection, refraction. To consider the propagation of light within an optical fiber utilizing the ray theory model, it is necessary to take account of the refractive index of the dielectric medium. The refractive index of the medium is defined as the ratio of velocity of light in vacuum to the velocity of light in the medium. A ray of light travels more slowly in optically dense medium than in one that is less dense, and the refractive index gives a measure of this effect. When a ray is incident on the interface between two dielectrics of differing refractive indexes, let us consider two different mediums called glass and air. The refraction occurs, and it is illustrated in this figure. It may be observed that the ray approaching the interface is propagating in a dielectric of refractive index n1 and is at an angle psi 1 to the normal on the surface of the interface. If the dielectric on the other side of the interface has the refractive index n2, which is less than n1, then the refraction is such that the ray path in this lower index medium is at an angle psi 2 to the normal, where psi 2 is greater than psi 1. And this angle of incidence psi 1 and reflection psi 2 are related to each other, and the refractive indices of the dielectrics by Snell's law of refraction, which states that n1 sin psi 1 equal to n2 sin psi 2, where n1 and n2 are the refractive indexes of medium 1 and 2, and psi 1 and psi 2 are nothing but the angle of incidence and reflections. Or this expression can be written in another form: sin psi 1 divided by sin psi 2 equal to n2 divided by n1. It may also observed that in figure, that is a small amount of light is reflected back into the original dielectric medium, that is a partial internal reflection. As n1 is greater than n2, the angle of refraction is always greater than the angle of incidence. Thus, when the angle of refraction is 90 degree, exactly 90 degree, and the reflected ray emerges parallel to the interface between the dielectrics, the angle of incidence must be less than 90 degree. This is the limiting case. The refraction and the angle of incidence, now known as the critical angle, called psi c. You can find it is in figure 1.2 b. From the equation n1 sin psi 1 equal to n2 sin psi 2, we can write sin psi 2 equal to sin psi c equal to n2 divided by n1. At angles of incidence is greater than the critical angle, the light is completely reflected back into the originating dielectric medium with a high efficiency, with around 99.9%. Hence, it may be observed that the total internal reflection occurs the interface between the two dielectrics of differing refractive indices when the light is incident on the dielectric of lower index from the electric of higher index and the angle of incidence of the ray exceeds the critical angle. This is the mechanism by which the light at a sufficiently shallow angle, that is less than 90 degree minus psi c, that is the critical angle, it may be considered to propagate down an optical fiber with low loss. The figure shows that the transmission of a light ray in an optical fiber via series of total internal reflections at the interface of silica core and the slightly lower refractive index silica cladding. The ray has an angle of incidence psi at the interface which is greater than the critical angle psi c, and the reflected and is reflected at the same angle to the normal. This type of ray is simplest to describe, and it is generally used when illustrating the fundamental transmission properties of the optical fibers. It must also be noted that the light transmission, which is shown in the figure, assumes a perfect fiber, and that any imperfections at the core cladding interface would probably result refractions rather than the total internal reflection, with the subsequent loss of a light ray into the cladding. So, having considered the propagation of light in an optical fiber through internal reflection at the core cladding interface, it is useful to enlarge upon a geometric optics approach with reference to the light rays entering the fiber. Since only rays with a sufficiently shallow angle, normally with an angle normal to the normal with an angle to the normal greater than the psi c at the core cladding interface, and are transmitted by the total internal reflection. It is clear that not all the rays entering the fiber core will continue to propagate down its length. So the geometry considered with launching a light into the optical fiber is shown in this figure, which illustrate a meridional ray. Normally the meridional ray follows a zigzag path at the critical angle psi c within the fiber at the core cladding interface. It may be observed that this ray enters the fiber core at an angle theta a to the fiber axis, and it is reflected at the air core interface before transmission to the core cladding interface at the critical angle. Hence, any rays which is incident into the fiber core at an angle greater than the theta a will be transmitted to the core cladding interface at an angle less than the psi c, and will not be totally internally reflected. This is what illustrated in this figure. Hence, the theta a or acceptance angle is the maximum angle to the axis at which the light may enter the fiber in order to be propagated, and is often referred to as the acceptance angle for the fiber. So the acceptance angle for an optical fiber was defined in the preceding slides. However, it is possible to continue the ray theory analysis to obtain the relationship between the acceptance angle and the refractive indices of the three media involved, namely the core, cladding, and air. This leads to the definition, normally more generally used term, the numerical aperture of the fiber. It must be noted that within this analysis, as with the preceding slides of the acceptance angle, we are concerned that with the meridional rays within the fiber. Here the figure shows a light ray which is incident on the fiber core at an angle theta 1 to the fiber axis, which is less than the acceptance angle for the fiber theta a. The ray enters the fiber from air medium of refractive index n0, and the fiber core has the refractive index n1, which is slightly greater than that of the cladding refractive index n2. Here we are assuming the entrance face at the fiber core to be normal to the axis. Then considering the refraction at the AR core interface, this can be expressed using Snell's law. R naught sin theta 1 equal to n naught sin theta 1 equal to n1 sin theta 2. Considering the right angle triangle ABC, here we are forming one triangle called ABC. It is the right angle triangle which is indicated in this slide. Therefore psi equal to pi by 2 minus theta 1, where theta is greater than the critical angle at the core cladding interface. Therefore the equation can be written as n naught sin theta 1 equal to n1 sin cos psi. Using the trigonometrical relationship sin squared psi plus cos squared psi equal to 1, we can rewrite the equation. So therefore n naught sin theta 1 equal to n1 into 1 minus sin square psi whole power 1 by 2. When the limiting case, the total internal reflection is considered, here the psi becomes equal to the critical angle for the core cladding interface. So therefore the equation can be rewritten n naught sin theta a equal to n1 square minus n2 square the whole power 1 by 2. Since the numerical aperture is often used to the fiber in the air where n0 is unity and it is simply equal to sin theta a, it may also be noted that the incident meridional rays over a range of 0 to theta a will be propagated within the fiber. The numerical aperture may also be given in terms of relative refractive difference between the core and the cladding, which is defined as del equal to n1 square minus n2 square divided by 2 n1 square. Otherwise this can be simplified, and finally we can write Na equal to n1 into 2 times of del the whole power 1 by 2. So far we discussed about the concept of optical rays propagation through the fiber. Thanks for watching.